Hello everyone. Today I'm going to discuss the alternative ways of designing an assembler under the topic assembler design options. So far in our earlier discussions, we have studied how to design and implement a two-pass assembler. As you all know, a two-pass assembler performs two complete scans over the source program in assembling the program written in assembly language. During the first scan, every instruction in the source program is assigned an address and all symbols are defined. While during the second pass, instructions are translated into machine language code and the object program generation is done. As an alternative to two-pass assemblers, we have two design options. First is a one-pass assembler and the second is a multi-pass assembler. In today's lecture, I'll be exclusively focusing on the design and implementation of a one-pass assembler. A one-pass assembler is one which translates the program written in assembly language to machine language by performing one complete scan over the source program. And a major problem in implementing a one-pass assembler is handling the forward references or references to symbols which are defined at the later part of the program. Although eliminating all forward references is not possible, eliminating forward references to data items can be easily done by asking the programmer to define all symbols before they are used in the program instruction. However, eliminating forward references to instructions cannot be easily done because programs require forward jumps, and asking the programmer to write program using only backward jumps is too restrictive because you may want to skip certain instructions in a program which involve a forward jump. A one-pass assembler can be classified into two types. We may design a one-pass assembler to produce object code directly in memory for immediate execution, and such kind of assemblers are referred to as load and go assemblers. The second type of one-pass assemblers produce usual kind of object program for later execution. We shall first begin by discussing how to design and implement a load and go assembler. That is an assembler which generates the object code directly in memory for immediate execution. In order to understand the design and implementation of a load and go assembler, we will consider a simple SIC program. In this particular slide, you see that the program is named set array and the program has been written using the SIC instruction set. We have written the program by eliminating majority of the forward references. As you see, all data areas have been defined in the program before they are referenced. However, as I mentioned earlier, not all forward references can be eliminated. As you see, we have two instructions which involve forward references. The first is JLT set 0. Set 0 is a symbol which is defined later in the program. Likewise, we have another instruction JLoop, and loop is a symbol which is defined at the later part. Now, assuming that majority of the forward references have been eliminated, we shall see how to generate the object program for this object code for this particular program. As I mentioned earlier, a load and go assembler generates the object code directly in the memory for immediate execution. As usual, the processing begins with the first instruction. The first instruction is an assembler directive, namely start. It specifies the name of the program set as set array, and the starting address is 1000. As this is an assembler directive, no object code is generated. Moving ahead, We begin by processing the first executable instruction. The first instruction here is 0 word 0. As we know, the starting address for the program is 1000. So the address assigned to this instruction is 1000. In other words, the instruction that we have here is 0 word 0, which generates a constant 0 in the memory. And the constant is generated at the address 1000. So the object code generated is the constant 0, which is 0, indicated using a 24-bit format. So in hexa, we represent it as 000000. So as I mentioned earlier, load and go assemblers generate the object code directly in the memory. So the first code generated is 000000, and at the bottom of this slide, I have shown the contents of the memory along with the address. You may see here the first row indicates the starting address 1000, the second row indicates the address 1010, and so forth. The columns indicate the consecutive memory locations respectively. For instance, we have 1000 indicated in column 0, address 1001 indicated in the second column, address 1002 indicated in the third column, and so forth. So the first object code generated is 000000, which is generated or placed in the memory at the address starting from 1000. So we have 000000. So after the first instruction is executed, the updated memory address is 100 plus 3, which is 1003. So at the location 1003, the object code generated will be, so we have the instruction 1 word 1. So the object code generated here is 000001. 1 in decimal is represented in hexa using this code. So you may see that this is loaded in the memory starting at the address 1003. So I represent it here 000001. Also, remember the assembler places every symbol that is encountered in the source program into the symbol table. So already we have seen 3 symbols. First is the set array with the value, the starting address, that is 1000. The second symbol was 0 with the address 1000 as well. The third symbol was 1 with the address 1003. So after processing the instruction 1 word 1, the updated location counter value is 1006. So the object code generated for the instruction 3 word 3 is 000003, which is the internal representation of 3 in hexadecimals. So we have not entered 3 into the symbol table. So 3 has to be entered with the address 1006. The object code is generated starting at the address 1006000003. The next instruction is 30 word 30, and the assigned location counter value is 1006 plus 3, which is 1009. We need to enter this symbol. So 30 has to be entered with the address 1009. Object code generated is the hexa representation of 30, which is 1E. So the code generated is 00001E. And it's generated in the memory at the address 00001E. The next instruction is 16 word 16. After processing the previous instruction, the location counter has to be updated by 3. So the updated location counter value is 100C. So we enter 16 into the symbol table with address 100C. The object code generated is hexa equivalent of 16, which is 000010, and it has to be generated in the memory starting at address 100C. The next instruction is index reserve word 1. So after reserving 3 bytes, the updated location counter value is 100F. So we enter index into the symbol table next. Index is entered along with the address 100F. Please note this instruction specifies that one word of storage has to be reserved in memory. So we don't have to generate any code here. Instead, storage has to be reserved. One word of storage has to be reserved. One word is equivalent to 3 bytes. So starting from 100F to 1011, storage will be reserved. So the next unassigned address is 100F plus 3. F1011, next address is 1012. So from 100F to 1011, the storage is reserved in memory for index. So you may see it here 100F, starting from here to 1011, storage is reserved. Following index reservoir 1, we have the instruction alpha reservoir 10. So we have a symbol in the label field. So symbol has to be entered into the symbol table with the updated address 1012. The instruction reserves 10 modes of storage. We have 10 modes is equal to 30 bytes, which is equivalent to 1E in hexadecimals. So starting from 1012 to 102F, 30 bytes of storage will be reserved in the memory. We may refer to it in the next slide. So starting from 1012 to 102F, storage has been reserved in memory. You may see it here with excess indicated or highlighted with green. The following instruction is LDA 0. So after 30 bytes of space has reserved, the updated location counter value is 1012 plus 1E, which is 1030. The instruction LDA 0 is encoded as 001000. LDA has an equivalent code 00. 0 has the address 1000. So the assembled instruction is 001000, and it is placed in the memory or generated in the memory at the address 1030. You may see it here at the starting at the address 1030. We have next STA index. So the object code has to be placed corresponding to STA index has to be placed in the memory starting from address 1030 plus 3, that is 1033, because we have reserved 3 bytes of space for the instruction LDA 0. You may see it here also in the memory representation. Already the code is filled till 1032. Next address is 1033. So starting from 1033, we generate the code for STA index. The following slide shows the representation for the remaining instructions. For STA index, the code is 0C100F. So you may see it here starting from the location 1033. The following instruction is 04100F, which starts in the memory at the address 1036. So it's being generated here 04100F. The following instruction is set loop LDA alpha X. So we have a label here, set loop, and the unassigned address is 1039. So set loop is entered into the symbol table along with the address 1039. The object code generated is 009012. The instruction indicates the indexed mode of addressing, so flag X has to be set to 1. So that is why we have 9 here. The flag X is set to 1. So opcode for LDA is 00. Following the opcode, we have the flag X. The address for alpha is 1012. So 1 here 1012 is represented as 0001 followed by 0000 followed by 0001 and 0010. So the first digit here is 1, which is 0001, but then uh, 0001 has to be changed to 1001 because the instruction indicates the index mode flag X has to be set to 1. So that is why 1012 gets changed to 9012. So we have to place this code in the memory starting at the address 1039. So you may see it here. We have kept it in the memory at the address 1039. So after processing this instruction, the next instruction to be taken is COM16. So the opcode is 2828 and 16 has the address 100C. So the object code generated is 28100C, and you may see that it's placed in the memory starting at the address 103C, which is here 28100C. The next instruction is JLT set 0. Please note, so far we have processed instructions which does not involve a forward reference. However, now we have encountered an instruction wherein the instruction makes a reference to a symbol which has not been encountered so far, or which has not defined in the symbol table so far. So the object code cannot be readily generated for this instruction. So we know that JLT is translated as 38. However, since set 0 is not defined in the symbol table, you cannot encode the instruction completely, or the entire code cannot be generated in the memory. So whenever a instruction refers a symbol which is not defined in the symbol table, the one-pass assembler enters the undefined symbol into the symbol table and sets its value as star, indicating that the value of the symbol is not known. Further, while the object code is placed into the memory, it just keeps the object code corresponding to JLT, that is the operation code, and it leaves the address field corresponding to set 0 empty. Also, to ensure that the value of set 0 is entered at the corresponding location at a later point, in the symbol table, the assembler maintains a list of forward references which contains the address of the memory location where the address has to be entered. Address corresponding to the symbol set 0 has to be entered. So you may refer to that in the next slide. So please note set 0 is undefined. So set 0 is entered to the symbol table and its value is indicated by star, meaning that the value is undefined. Further, the assembler maintains a list of forward reference, and the list contains the address of the operand, address of the memory location where the symbolic operand set 0 has to be kept. Address corresponding to set 0 has to be kept. So what is the address corresponding to set 0? Please note that the instruction JLT set 0 begins in the memory at 103F, that is, it begins at 103F. However, the address field is not known. So the address corresponding to this address field is one more than the address 103F, which is 1040, which is 1040. So this address 1040 is added to the list of forward reference associated with the symbol set 0. And while the instruction is generated in the memory, as I mentioned, 38 is entered and the remaining 2 bytes will be left empty, indicating that the address corresponding to set 0 is not known. At a later point, when the value for the symbol set 0 is known, or in other words, when set 0 is defined, its value might be inserted at the address that is indicated in the forward reference list, that is 1040. In the memory, it's shown here with the dashed lines. Moving ahead with the processing further, the next instruction is LDA1 and the object code generated is 001003, which has to be inserted at the address 1042. So you may see it here. It starts at the address 1042 and goes on till 1044. The following instruction is STA alpha, x, which begins in the memory at 1045. So you may see it here, begins at 1045. So after processing STA alpha, x, the updated address for the next instruction will be 1045 plus 3, which is 1048. So we should proceed ahead with the processing of the next instruction, that is jump loop, and the address here is 1048. The instruction has been shown with the green background because this is again an instruction which involves a forward reference to a symbol that is defined later. So we have loop defined after it has been used in the instruction. So since the instruction involves a forward reference, we cannot completely assemble the instruction. So opcode is generated for jump, which is 3C, and the address field is left empty. So here we have indicated with dashed lines. Also, since the value for the loop is unknown, it is entered into the symbol. The assembler enters it into the symbol table. However, since its value is not known, it is indicated as star. While value is indicated as star, or the entry is flagged to indicate that the value for loop is unknown. In order to enable the actual value of loop to be inserted at the later point at the address 1049, a forward reference list associated with loop is kept which saves the value 1049, which is nothing but the address corresponding to the memory location where the value of loop needs to be inserted. This corresponds to the address 1048 plus 1, that is 49, because 1048 contains the opcode 3C. Also, the instruction is placed into the memory by leaving the address field empty, and you may see it here, it's being highlighted. So at the location 1048, we have inserted 3C with 2 bytes empty. Proceeding ahead, the next instruction to be processed is set0 LDA 0. You need to pay attention at this point because the instruction has a symbol set0 which is already entered in the symbol table, and it was marked as star, or it was flagged indicating that the value is not known. Right now the value for set0 is known, it is 104B, that is set0 is defined at this point. So star can now be replaced with the actual value of set0, that is 104B. Also, the forward reference list associated with set0 has to be scanned, and the value of set0 is 104B, has to be inserted at the address 1040. So in the memory, you may see it's somewhere here. 38 is the opcode, and we have left the address field empty corresponding to set0. So at this point 1040, the value of set0 needs to be inserted. So we have replaced star with 104B. Now the forward reference list has to be scanned, and at 1040, the value for set0 has to be inserted. The following slide shows it. So you may see that at the address 1040, the value for set0, that is 104B, has been inserted. Since the forward reference list is already scanned and the entry is being made and the update is done, now this list can be deleted. So in the next slide, you may see that the forward reference list associated with set0 has been eliminated. And we proceed ahead with the processing. The label is processed. Next we have the instruction LDA0. So object code can be generated for this instruction. So in the next slide, you may see that the object code is generated for LDA 0 and it has been inserted at the address 104B. It's inserted. The next instruction is also inserted likewise. So you see it 0C9012. The next instruction has also been inserted starting at the address 104E. It's at this point. Proceeding ahead, the next instruction is loop LDA index. Now we have a symbol here. The symbol is already present in the symbol table. However, its value is undefined. It was not known earlier. So since loop is defined at this point, the value here is 1051. The symbol table can be now scanned and star can be replaced with 1051. So you may see that the symbol table entry is now changed from star to 1051. So there is a forward reference list associated with loop. So the value for loop has to be inserted at the address 1049 as was done for set 0. So at the address 1049, we need to insert 1051. It is actually indicated here. It's highlighted in blue. You may see that 3C was an opcode corresponding to J. However, value for loop was unknown. Now its value is inserted at the address 1049. So since value for loop is now known and the forward reference list has been scanned, this list can now be eliminated because we have already done the updation. So at this point, the assembler eliminates the forward reference list associated with loop and the processing proceeds ahead. The instruction to be processed next is LDA index. The object code generated is 00100F. Please note it is inserted into the memory starting at address 1051. Likewise, all the rest of the instructions are processed until the end directive is reached. So in the further processing, you may see that the instruction add 3, STA index, come 30 and JLT set loop are processed and the rest of the object codes have been inserted in the memory starting from the address 1054. So the last instruction is 381039 corresponding to JLT which begins in the memory at 105D. So you can see it here, it's 381039. So after this instruction is processed, the updated address is 1060, which is the length of the program, and the directive here is end, which indicates the end of the processing. So by this time, the one-pass assembler would have placed the entire code into the memory and necessary storage space would be reserved. So this is all about the one-pass assembling as far as load and go assemblers are concerned. So as far as the implementation aspects are concerned, you may see that a one-pass assembler generates the object code for the instructions as it scans the source program. Whenever an instruction involves an operand that is a symbol which is not yet defined, the operand address will be omitted at the time of assembling. And the symbol whose value is unknown is entered into the symbol table and the entry is flagged with star to indicate that the symbol's value is not defined yet. At a later point, also a list of forward references maintained associated with the symbol whose value is undefined. And this forward reference list contains the address of the operand field for the instruction that references the undefined symbol. When the definition for the symbol is encountered, the list of forward references for that symbol is scanned and the value of the symbol or the address that is associated with the symbol will be inserted at the address that is indicated in the forward reference list. Next 5 to 6 slides discusses at another example of a one-pass assembler with a different example. The example that is discussed here is taken from the textbook. You may go through the slides and try to understand how a one-pass assembler works in processing the program. The program is actually written using the SIC standard version, instruction set available in the standard version. Please try to go through the program and try to understand the concept further. So that is all about a one-pass assembler, which generates the code directly in the memory for immediate execution. The second type of assembler is a one-pass assembler that produces the usual kind of object program so that it can be executed at a later time. So I am going to discuss now the second type of assembler that generates an object program in the memory. However, the assembler performs only one scan over the source program. We will consider the same example as was discussed earlier. All reference data items, all symbols have been defined before they are referenced in the program. This is done to avoid forward references as much as possible. We have taken the same example. Now, as far as processing of the source program is concerned, we always begin with the first instruction, that is set array start 1000. So remember, this is an assembler which generates the object program. As the start statement is processed, the header record will be initiated, which begins with H followed by the name of the program. We use 6 columns to indicate the name. So the first 6 columns are shown here, and the starting address is 1000. Following the starting address, we have the length. However, the length is not yet known because until we reach the end directive, length is not known. So length field is left empty. Next, the following instructions are processed one by one. And as the object codes are generated, they are written into the text record. So in this particular slide, you may see that the instructions starting from 0 word 0 to 16 word 16 have been processed, and the corresponding object codes have been kept in the text record. As you know, the text record begins with T followed by the starting address of the object code that is kept in the current text record. The first object code that we place in this text record is 000000, so which is here, and the starting address is 1000, so it is here. So we have after T we have the starting address. After that, we have to keep the length. Length is known only when you reach the end of a particular text record. So we have kept 1, 2, 3, 4, 5 instructions. Each one occupies 3 bytes. So 5 into 3 is 15 bytes. So the length here is 0f. Please note, we have to terminate the text record at this point because following instruction is index reserved 1, which reserves space in the memory. So object code terminates at this point, so the text record is terminated at this point. For all the object code that follows, we have to initiate a new text record. The symbol table entries are also shown here accordingly, which is maintained in the same way as was done in the case of load and go assemblers. Address assignment is also done as was discussed in the earlier program. Proceeding ahead, so after storage space is reserved, the next instruction is LDA 0, which begins in the memory at 1030. So the rest of the instructions are processed same way as was discussed earlier until come 16. So LDA 0 is encoded as 001000. 00 is the opcode for LDA. 0 has the address 1000. So this is object code. Similarly, STA index, STA has the code 0C. Index is having the address 100F. So object code is 0C100F. So all these codes are kept into the text record. And the first code here is 10001000, which is having the address 10330. So you may see that the text record specifies a starting address 1030. This is a starting address, and all object codes are kept into memory into the text record 001000 to 28100C. So after that, we still have few instructions. You may see that there are still furthermore instructions, but at this point, the text record generated is T followed by the starting address followed by the 5 instructions. Thereafter, the next instruction is JLT set 0, which can also be kept in the same text record. But at this point, you need to pay attention because this is an example of forward reference. And as was handled by a one-pass assembler, at this point, the assembler has no idea what is the value for set 0. So it enters a set 0 into the symbol table. The processing is same as in the case of load and go assembler. Star is inserted indicating that the value of the symbol is unknown, and the forward reference list associated with this entry, that is set 0, is kept, which is one more than the address corresponding to the instruction 103F plus 1, which is 1040, because at location 103F we have 38. The next address, the address corresponding to operand is 103F plus 1, that is 1040. So that is added to the list of forward reference. And please note, when the object code is kept into the text record, we don't leave it empty. Instead, since the value for set 0 is not known, we insert 0 in the place of unknown value. Because set 0 is not defined, we insert zeros here. Later, when the value for set 0 is known, a new text record is created and the address corresponding to the memory location where the value set 0 has to be inserted is placed in the text record. So proceeding ahead, the next instruction is LDA1, which is generated, which is kept into the same text record, because you know that in one text record we can keep at the most 10 instructions. The following instruction is 0C9012, which is also kept in the same text record. Proceeding further, the next instruction is J loop. So this instruction again involves a forward reference. So we don't know the value corresponding to loop. So loop will be entered into the symbol table and it will be flagged as star, indicating the value is unknown, and the address of the symbolic operand field is entered into the symbol table, which is 1048 plus 1, and it is saved in the forward reference list as was done in the load and go assembler. So once this is done, the object code is added into the text record. So please note, the value for loop is not known, so we insert zeros in the place corresponding to the symbolic operand loop. So after this instruction is processed, the next instruction is set 0 LDA 0. So the next instruction is set 0 LDA 0. We have a label. Label is already present in the symbol table. However, its value was earlier not known. Now, since the value for set 0 is known, we have to create a new text record saying that the value for set 0, that is 104B, has to be inserted at the address 1040. So you may see that we have indicated it here. In the symbol table, you replace star with the value for set 0, that is symbol is currently defined. So insert 104B corresponding to set 0, scan the forward reference list associated with set 0, and create a new text record corresponding to this instruction, because we earlier had an instruction, just going back, the instruction was JLT set 0 and the object code generated was 380000. We inserted 0 because the value was not known, and we had kept the address where the value for set 0 has to be inserted in the forward reference list. Now that we know the value for set 0, we have to create a new text record saying that at the address 001040, you need to insert the value 104b, which means after 38, we need to insert 104b, which corresponds to the address 1040. So please note, earlier when the value was not known, we had inserted 38 followed by zeros indicating values are not known. Now when the value for set 0 is known, we initiate or create a new text record saying that the value of set 0 has to be inserted at the address 1040. So T followed by starting address is 001040. 02 indicates the length. What is this length? This indicates the length corresponding to the symbolic operand. Loop has the address, the set 0 has the address 104b. So 104b is represented in hexa and this requires 2 bytes. So we indicate it here, length is 2 bytes. So we are done with the processing of the label. The next part is the processing of the instruction LDA 0. So after the record T has been generated to show the updations, next we generate the object code corresponding to the instruction LDA 0, which is 001000, and it is written to a new text record. So you may see it here, it's 001000, and the address is, this instruction has to be placed at the address 104b. So the text record indicates the starting address 00104b, where we keep the object code 0001000. So after that, the next instruction is STA alpha comma x, which is placed at the address immediately following 001000, which is 0C9012. So after that, the next instruction is again loop LDA index. Now again, we have encountered a symbol whose value was earlier not known, now it is known. So we have to terminate this text record and we have to insert a new text record saying that the value of loop, that is 1051, has to be inserted at the address 1049, because we had kept zeros in the memory location 1049 where we were supposed to insert the value of loop. So you may see it in the next slide. So the current text record is terminated and a new text record is initiated, which says that at the address 1049 insert the value of loop, that is 1051. So we are done with the processing of the label. Proceeding ahead, we need to now process the instruction LDAX. So object code has to be generated. So at the location 1051, in the text starting with the starting address 1051, we place the object code, that is 00100F. The remaining instructions are accordingly processed and entered into the text record. The following instructions are 181006 to 381039, which are shown immediately following 00100F. Finally, the length has to be indicated. Please note, the lengths have to be indicated in every text record before moving ahead with the next text record. So here the length is 3 plus 3, 6, 9, A, B, C, D, E, F. Length is 15 bytes, so length has been indicated. Next, the last statement processed is end. By this time, we know the length of the program, which is 1060. So end record is written and also the head record is completed by adding the program length. So that is all about the one-pass assembler, which generates the object program for later execution. the processing is same as for load and go assemblers, except that in this case, as the object codes are generated, they are written directly to the text record. And whenever a symbol is undefined, it is entered into the symbol table and flagged with star indicating that the value is unknown. Forward reference list is maintained, which holds the address of the memory location where the symbolic operand's value has to be inserted. Later, when the definition for undefined symbol is encountered, the current text record is terminated and a new text record is written indicating what is the value of the symbol that has to be inserted at the indicated address that is given in the forward reference list. So that is all about a one-pass assembler that generates the object program. You may go through the example that is discussed in the textbook and try to understand the concept with the different example as well. For any clarifications, you may post the queries in the canvas. So that is all about one-pass assemblers. So the only topic that is left out in assembler is the multi-pass assembler, which will be discussed in the upcoming videos. Thank you.